So I have realized there might be a gap between what I'm teaching you and what the rest of the lectures. So if you have any questions, please come back to me after this last talk and I can answer. So yesterday, what we have seen is a little bit of introduction about the history of the field, the detectors, what we have done so far, and I have illustrated my explanation with, of course, pictures of the last year discovery. So now, what I'm going to do today is to go a little bit more into details on how we search for compact binary sources. And I will explain I will provide you with some illustration of the kind of physics we can do, especially the test of general relativities that we can do with those gravitational waves emitted by a compact binary system. So how we detect the signal in the data. So I should take So remember, we have a detector. We have several, actually. We have at least 2 or 3 detectors. And what we measure in the detector, so what we measure is when a gravitational wave is passing through the detector, what we are trying to measure is the perturbation of the metric, the local metric. How we do that is by measuring the light phase shift due to the change of the metric when you have photons traveling into the 2 arms of the interferometer. You expect, if the metric is changing, you expect a differential effect in the 2 arms and thus a phase shift of your recombined beam on the photodiode. So we are expecting from time to time, when we have such events passing through the detector, to observe a change of the phase of the light in the detector. What we actually, the signal we are measuring, so it's a power on a photodiode, which is converted, calibrated into a strain amplitude, H. But plus noise, of course. What we are measuring is noise plus, from time to time, this strain amplitude, which is actually the projection of the 2 polarization on the antenna pattern of the detectors, meaning the detector has a special response which is different for the 2 polarization. So what we are measuring is a linear combination of the projection of the 2 amplitude polarization. And those functions, the response of the detector to each polarization is shown here. And you see that they are completely different. They are different. They have some similarities. For instance, here you have the 2 arms of the detectors, by the way. And of course, this is symmetric in terms of Z. If I call this the one arm X and the other is the other Y. But you see that the answer for the 2 polarization is different. And what you can see, this is what I was mentioning after the lecture yesterday to some of you, is that there is a blind direction. If you have a wave, this is a combined, if you consider the square of the 2 response function, there is a blind, you obtain this antenna pattern, and there is a blind direction, where if the wave is coming along the diagonals of the detectors, we don't see, the answer of the detector is 0. That means we are not going to detect anything for the 2 polarization. So this is something which is illustrated here, where you have the sky coverage. This is what you see is a representation of the sky in some, here it's in some, Sorry?
So on the previous plots, there was, so the directions of the arms is clear, but what is the height or what?
If I have 2 arms like that, it's the Z. It's We are on Euclidean geometry, x, y, and z. So it means that if I have a wave coming perpendicular to the two arms, the answer of the detector is maximal, actually. This is what this diagram is showing. The length of this surface, or the height of this surface, I don't know how to say that correctly, is giving you the amplitude of the response. Meaning if you have a wave, when the wave is coming along z, then the amplitude is maximal. If the wave is coming along the diagonal, it's going to go, it's zero, actually. This is what this antenna diagram is telling you.
I think another answer to this is that you take a direction and you plot how sensitive you are to a wave in this direction. So this is the graph of this function f squared plus f squared, is it? At each angle, right? So the surface is just the value of this function.
Yeah.
So if it's 1, you're fully sensitive. If it's 0, then you don't see the wave coming.
So if it was isotropic sensitivity, this would be a sphere.
That would be, yeah, exactly, that would be a sphere, yeah. But we have, yes, exactly. And we have one answer, one antenna for each polarization. So it's a little bit complicated because you have a linear combination of the two polarization. And in other words, we are not sensitive the same way to both polarization depending on the source. The point is that the detector is on Earth and the Earth is rotating. So it's a complication that we need to handle, but it's not so difficult. And what it shows is actually typically this quantity here, the square of the two antenna function as function of the coordinate on the sky. And what you see is that there are some maximal region for two detectors, if we consider, because then you can consider, when we work on network, we need to consider the response of the two detectors. This case is for the two LIGO detectors, though they are not perfect, they are not on the same site. They are more or less aligned, so they see at a given time almost the same part of the sky. And when you add, so here you have the red spot are the maximal amplitude response, and the blue are the minimal. So you see, we have at a given time some blind spot of the sky. That means that we are not going, with these two detectors, we are not going to be sensitive to a source which is localized here at that given time. If you add Virgo, you see that you obtain more or less something which is more uniform. The blind spot disappeared, more or less. And this is because Virgo is not aligned with respect to LIGO. And it covers part of the sky that are not covered by LIGO. And if you add more, I was talking about yesterday that there are some detectors on construction in Japan and some plan in India. If you add more detector, you see that you obtain an almost uniform response over the sky. So the more detector you have, the better it is to be sure that we are not going to miss a source that is happening somewhere in the sky. So let's go to the detail of the analysis. So as I was telling you, what we are measuring is noise. And the basic assumption we're doing is that on top of the noise, from time to time, we have a gravitational wave signal. So the noise is just a time series, just a sample at a given frequency rate. It's not white, it's not Gaussian, and it's not stationary. So we need to have there are lots of processing of the data that is required to really being able to extract the signal. So especially the nature of the noise is something which is handled by a team of physicists which would try to really understand each part of the basic characteristic of the noise. So we have lots of tool to do what we call the detector characterization. And I was mentioning, so one thing which is important to know is the sensitivity of the detector. One way to sensitivity to a given signal. So one way to measure the sensitivity is to look at the spectral density noise of the noise. So this is what is represented. And yesterday I was telling you this is just the Fourier transform of the autocorrelation function of the noise. So we take, to build such kind of curve, actually it's not a mystery. You take the data, your time series, you autocorrelate, it means you compute the autocorrelation function of your noise. I mean, you take the time series and you multiply it by itself. And then you take the Fourier transform and you obtain almost those curves. So for the CBC search, the compact binary system search, what we'll count is a full band. There are signals that we expect at a given frequency. In that case, what is very important is to have the best sensitivity in that given frequency range. For compact binary signal, we expect to have the signal entering the band and up to, finishing the coalescence and at the end merging inside somewhere in the band. So we need the full frequency band. So yeah, I'm going to skip that. So I was talking about, so we do a lot of Fourier transform. So this is a basic signal processing of the signal is to do, we constantly, pass from the time domain to the frequency domain, and to do that we use a Fourier transform. And we are not using, the standard Fourier transform. What we are using quite a lot is the discrete Fourier transform, and actually behind the discrete Fourier transform, what we're using is some special algorithms that are very fast, because you have to understand that we are acquiring data 24 hours and every day, so we have lots of data, and to process those data, you will see that it's really time-consuming, so we need to have a very efficient algorithm to process the data. But this is this is a basic, I would say, the basic signal processing algorithm is the Fourier transform.
So I have a question.
Yes.
When you Fourier transform, you're integrating over the whole arm, and obviously here you're sampling.
No.
So how does this?
Exactly. Actually, the point is that we are not. So we have time series, we have segments of data. So what we're doing is so normally we have an infinite time series. This is not the case because from time to time the detector are not locked. So that means we have no data. So we have segments of data. We split the segment of data. We Fourier transform them, and we recombine. There are ways to treat correctly the boundaries.
So you're replacing the integral over R to a finite integral?
Yes,
or
and this is
wavelengths or what?
Windowing. This is a key word, actually. And this is the subject of this slide, actually, because this is very important. I was telling you, the noise power spectrum is a Fourier transform of the autocorrelation function. So this is the formula where you see the autocorrelation function, and you take the Fourier transform. I told you that what we are doing, we are working in the discrete domain. We don't have a function, but we have sample of data. So what we are doing is to compute what we know is that if you have an infinite time series, this function is equivalent, thanks to the Wiener-Kirchner theorem, to the square of the Fourier transform of the data. It's easy to demonstrate that. But this theorem, so you will tell me that it's easy to compute a noise spectrum. I just need to take the Fourier transform of the data, I take the modulus, and that's all. If you do that, you're going to have a totally biased estimation of your noise spectrum. This is wrong. One of the basic reasons this is wrong is that this theorem is only correct if you have an infinite time series, if you have no boundaries, and which is not the case. I told you we have stretch of data that are not infinite, and sometimes we have only 200 seconds. But if there is a signal in 200 seconds, we need to analyze it. So we need to have some methods to be able to compute correctly the power spectrum. But by the way, what I'm telling you about the power spectrum is true for any signal processing, as long as you're trying to go to the Fourier domain. So these are the basic things. And so as I told you, so in reality, we have a finite amount of data. So the PSD, if you do that, actually, what does it mean? Is that here you should introduce a kernel function, which is a square function. This is what it means. That means your integral is not from minus infinity to plus infinity. It's from minus T1 to T2. And that means you're going to combo. What you're doing now, if you just do the Fourier transform, is that it's not the exact Fourier transform, but it's a Fourier transform convolved with a square function. And this is not correct if you do that. So to avoid this problem, there are many in the literature on signal processing. There are different ways to do that. And the basic one, which is working actually very well, is to, instead of taking your data, x of t, you multiply, so you have a stretch of data, finite stretch of data, and you multiply this stretch of data by a window function that goes to 0 at the boundaries. And this is the secret of actually signal processing when you deal with Fourier transform. And this is exactly, I come back to the Creswell paper we were talking about. This is the kind of thing they forget in their analysis, because obviously they still have to learn about signal processing. That's a parenthesis. So there are ways, so this is, so the basic signal processing in gravitational wave data analysis is Fourier transform. There are some very efficient, I'm trying to give you the takeoff message actually. So there are some very efficient algorithms to go very fast to compute a Fourier transform, but you have to pay attention to condition correctly your data, because the reality is that we are dealing with a finite amount of data, but so this is, there are some different methods. The windowing is the simplest one, and it's working very, very nice.
So I have to continue in the same vein.
Yeah.
So if you look at the gravitational wave detection paper, there is this diagram where there is a Fourier spectrum changing in time, right? So the frequency of the wave is changing in time.
Yeah.
But this doesn't make any sense, because a Fourier spectrum is the whole time.
Yeah, so this is the next.
This is some kind of windowing again?
No, this is the next.
Okay.
This is time frequency representation. It's another way to look at the data. So so far we have done Fourier transform. That means I take some data, stretch of data, and I change domain. From time domain, instead of looking at time series, I'm going to look at the frequency components in my time series, but it's static in some sense. It's a one-shot picture of your data. Another way and this is what you were talking about. Another way to represent the data is to try to see the evolution in time of the frequency components, and this is what we call time frequency representation. And the most simple time frequency representation is what we call a periodogram. And a periodogram is just a Fourier transform at a given time, And then you just add as function of time another Fourier transform and so on. So in the end, you see, so what you see, so here it's a time frequency representation. So here you have time and here you have frequency. And it's just a piece of slice of Fourier transforms that are added as function of time. And you see, thanks to that, you can see the time evolution of a signal. Here, it's illustrated with a signal, a binary black hole merger, where you know, so this is a waveform in time domain. You know that the amplitude is increasing as function of time, and the frequency is also increasing. You see it by eyes in time domain, but you see it even better, the frequency evolution in a periodogram.
So this is moving this window?
It's a periodogram is just, yeah, it's how to say that? It's Fourier transforms that are just put one after each other, and you obtain.
Integrating all the whole time.
No, what you do. So what you do is actually. So more details. What you do is you take your time domain data. You will take a window. For instance, I take 200 seconds. I will compute my Fourier transform over 1 second. I will obtain a Fourier transform. I will obtain then a column in this map. Then I will compute the Fourier transform of the next 1 second, and so on. So, and you can do more complicated things like moving windows, and there are lots of techniques to do that. But the periodogram is the simplest, say, time frequency representation. Here, actually, it's not a periodogram. I've cheated. I lied. This is not it's another type of representation. More or less, it's not really wavelet. It's basically a wavelet transformation of the data. So the principle is the same, but instead of doing a Fourier transform, you apply a kernel. Again, you do Fourier transform, but plus you convolute your data with a special function that will stretch. I mean, that it's just to have some, we say, the point with the Fourier transform is that your frequency resolution is fixed. It's fixed by the duration, the total duration of your data stretch. I mean, if you take 1 second, and if your data are sampled at a given frequency, you know that your minimal frequency resolution is going to be the frequency, sampling frequency divided by the duration of your data. So it's the Fourier transform is a fixed time resolution time frequency transformation. But so the wavelet, interest of the wavelet transformation and all this stuff is that you have multi-frequency resolution, and you can so you can, when you have a signal, and which is the case, when you have a signal for which a frequency is changing with time, it's interesting, because here, for instance, you see that the frequency is not moving a lot, while here it's changing very quickly. So you want to have more resolution in frequency here than in here. That's why wavelet transformation are interesting for in our case. So we do, what I wanted to say is that we do lots of type of signal processing. And yeah, but the Fourier transform is a very basic one. I hope it answered to all your questions. I haven't, yeah.
But like, as you said, if you just analyze every 1 second,
yeah.
Are you not losing some frequencies like much higher, or not much higher, but much lower frequencies? Like if the frequency is much bigger than the time that you're evaluating, you might not.
Right, but depending on typically the duration of your stretch of data will at a given sampling frequency, because our data are sampled at 16 kilohertz. But so if you have a duration t of your data, it's going to fix the frequency resolution. I told you it's F0 over, it's a Nyquist theorem. So if my data are sampled at F0, my frequency resolution is going to be F0 divided by the sampling number. That means the number of samples I'm going to take, so which is proportional to the duration. Okay, this is the number of samples, so it's equivalent to take t. And so this is fixed by the sampling frequency and the duration. So if you want to analyze, if you want to have a very good frequency resolution, you need to take a very large amount of data. This is what it means. And if you don't care about the frequency resolution, you can take a very short amount of data. And for instance, 1 second is very short. I mean, 1 second is you're going to have a 1 hertz resolution, typically. So it's very short. Yeah. Yeah.
Where does this F0 coming from?
Sorry?
Where does this F0 coming from?
F0, this is the sampling rate of our data acquisition system. And remember that our frequency, so this is a sensitivity, which is sample, actually the frequency in LIGO, it's 16, the frequency of the data acquisition is something, it's a power of 2 hertz. That means in 1 second we have 16 kilo samples. This is what it means. This is fixed, and we don't need to sample at higher frequency because you see that the sensitivity of those detectors are limited. And actually, at higher frequencies, there are other problems. I mean, the response of the detectors is going down. I mean, so this is well enough, and this is we don't need to go above. And most of the signal, there is not a lot of signal actually at higher frequency, so we don't care. Okay, more questions?
This particular number is
it's a power of 2. The reason why is that for many years, all the Fourier transform fast algorithms were more efficient with power of 2. That's the reason why. But now, actually, the newer generation of algorithms, there is not a big difference. For instance, in Virgo, the sampling frequency is 20 kilohertz. So, and it does not really matter. So we don't have the same sampling frequency. But yeah, people are used in signal processing, people are used to work with power of 2 especially because of the old generation of the Fourier transform algorithm. All right, so yeah, there's something, so I don't know where I am. Power, yes. Match filtering, yes. Then now, I already mentioned that the match filtering is the way we extract, actually, we extract a signal when you know the waveform. Because so far, the representation, I was mentioning Fourier transform or time frequency representation, I was not assuming anything about the signal. I was not saying, oh, the signal should look like something like that. No, I was just taking the Fourier transform of the data. Now, the case of the match filtering is the best, what we say, optimal filter. This is only true when you have Gaussian noise, actually. But this is indeed the optimal filter when you know the signal you're looking for. So the theory, again, is very simple, is that you always assume that in your data you have noise plus a signal. And what you will do is to autocorrelate, or you will correlate the data with a filter, K. So X is my data, and I will compute the correlation function of my data with a given function that the filter, K of t. So this is in time domain. The point is, what is the optimal filter that will maximize the correlation function? So actually, the answer is that this okay, so to find the optimal filter, what you do again is you go to the frequency domain. So this is so you take the Fourier transform of so this time domain expression is equivalent to this one in Fourier in frequency domain, and so that means you compute. So you take the Fourier transform of your data, your Fourier transform of your filter, and you multiply by the Fourier coefficient. And then what you will try to do, actually, when I was saying that you try to maximize the correlation function, it's not true. What we are trying to maximize is the signal-to-noise ratio. And the signal-to-noise ratio is the output of the correlation of your correlator divided by the variance of the noise. Here, this term is just the variance of the noise that you can compute, where the variance of the noise is just, you take here what you see is, what you find here is the Fourier transform of your noise. That means here I don't have any signal. It's equivalent of taking, again, I just take the Fourier transform of my noise, and where I assume there is no signal. And what you can see, what you can show actually, is that the SNR, the signal-to-noise ratio, is always lower than this integral, which is, so I should come back to this formula, which is the correlation function when x and k is equal to the signal I'm looking for. So it's always lower, and it's maximal. The SNR is going to be maximal when k is equal to the signal I'm looking for divided by the power spectrum of the noise. And finally, the final function, actually it's not C here, but it's rho, it's SNR function. So again, here what you what I forgot to mention is that it's a function of t. So it's just the integral of the data multiplied by the signal divided by the noise, by the noise spectrum.
Can you say again what is Sn of that? So, so x is the signal that you see, right?
Yes.
X theta is this Fourier transform.
Yes.
H is the expected signal.
Yes.
By what is Sn?
N, you mean?
Sn.
Sn is a noise power spectrum. So, yeah, that's it. That's it. That's the PSD. Sn, yeah, the notation of the, sorry. Yeah, it's modulus of the Fourier transform of your data. That's the noise.
It's squared?
No, it's an amplitude, sorry. It's square root of that, actually. No, it's a power. Power means it's going to be the square of, it's exactly that. And in the SNR formula, it's really the power, because you have, actually it must be homogeneous. So you have the product of two terms and should be a power in the denominator. So it's really the power. So it's really the square of the Fourier transform of the data, assuming there is no signal in your data. And this is the point. We need to have an estimation of the power spectrum of the noise when we have no signal. If you take your data when you have a signal, your PSD, your power spectrum, is going to be affected by the presence of the signal. So the PSD, the power spectrum, needs to be estimated at a time where there is no signal. So it's another complication. So the point, the estimation, that's why I was trying to insist a bit on that, is that the estimation of the noise spectrum is something which is fundamental. Because if you include part of the signal, but you will see it clearly, easily, is that if in your power spectrum there is part of the signal, since you divide the correlation, your correlator by the power spectrum, you will diminish the signal-to-noise ratio. So your power spectrum must be estimated with data that does not contain any signal. Otherwise, it's biased, or you underestimate actually the strength of your signal.
So your SM is not like the actual measurement, but it's coming from the estimate of the data?
It's an estimator, yes.
Estimate of the
and usually,
things which happen.
Typically what is done, because I told you the noise is not stationary. So if you compute your noise spectrum at a given time and you take another stretch of data, you will see that you don't have the same noise spectrum. So what we do is we compute the noise spectrum over basically all stretch of data, and we average. Such a way, normally if you have a transient signal, the fact that you take the average should wash out the signal in the average. And in addition to that, if you have, for instance, some noise at a given time, it should also wash out the effect of the noise or the non-stationarity, because the data are not stationary. You have a fluctuation. You have, and on very short time scale. I mean, it's not on a daily. Sometimes it's not on a daily time scale. You can have a huge variation of the sensitivity of the noise spectrum at a given time in the data. So the periods of data that are really bad, for instance, where the sensitivity is really bad, they are not considered for data analysis. They are especially for the estimation of the noise spectrum. So in one hand, to have a signal SNR computation which is correct, you need to have an estimation of the noise that follows the quality of the noise, but you don't want to be affected by glitches, by spurious noise that you have from time to time. So it's a trade-off. And it's what makes actually the whole process complicated in the end.
So this is not deterministic, but
it's
an art to do this.
It's absolutely odd, because you need to understand, the time scale of the variation of the noise, many factors. You need to understand the quality of your noise. I told you there are lots of people that will tell that everything about the data is recorded. For instance, when something happened somewhere around the detector, it's recorded. So we know, we have always means to understand what happened at a given time, at least up to a certain degree, not everything, but up to a certain degree, we know what's happening in the data. To understand, this is very important to understand when we have a signal, to understand if it was caused by a problem with the detector, the problem in the control, or if it's really a gravitational wave signal. So this is something. So in reality,
The changing noise would be, for example, a year ago when the waves change on the wave pattern changes on the nearby shore. Is this what you're saying, that the noise changes, right?
Yes.
It's not stationary. So Virgo, what change of the sea nearby would affect this? This is the kind of things that...
Yeah, so depends on which kind of noise. So yes, for instance, it's a good example is the seismic noise, because there's one thing that is well known, is that if your noise level during the day is higher than during the night. And the reason is human activity. in the city around the detectors. So, and this is something, so we know that, but it affects mainly the low frequency, the seismic noise. So not really, seismic noise is not playing a role. Seismic noise, so we see daily variation in this region because of the human activity. It's going to be affected. Here it's more, for instance, temperature variation, because here we are limited by the thermal noise, and we know that it's correlated with, it's not completely understood how the temperature of the mirrors is coupling. But here, yes, if, for instance, you will see variation, if the variation in the, in the vacuum chamber, if the temperature is varying inside the vacuum chamber, you will see some changes here. But then you have, in this region, you have also the control noise. And for instance, so it's purely, what I didn't mention yesterday is that we control the mirrors. I mean, the cavities, the different optical cavities are locked. That means that the mirrors cannot move. If they move, they have to move all together, typically. And because the light must resonate in the cavities to keep the maximal of sensitivity. But the mirrors, so they are controlled longitudinally and also in angular, over their angular degrees of freedom. And this is very difficult. It's quite difficult. And usually we have misalignment, and it's very slow drift over hours. And we see and so we are able to keep the alignment control, but again, up to a certain degree. So we see the drift, and usually we see the change of insensitivity because of this drift. So from time to time, people need to realign the mirrors to fix the sensitivity. So you have change of sensitivity. And the time scales are completely different depending on the noise source. Alignment, it's over hours. Seismic noise, it's going to be daily, so it's complicated. So I want to show you here how match filtering is working in it's an illustration of how it works. So here you have, in blue, you have the data, time series. So I'm telling you, I told you that the match filtering is, what you do is you convolute your data in Fourier domain with a filter, which is the signal, which is a waveform you're looking for. So in red here, it's the signal I'm trying to look for in my data. So by eyes, I'm not sure you would be able to tell me where the signal here is in the red data stream. And on this plot, you will see. So at each time sample, I'm going to compute the signal to noise ratio. If I'm able to, yes. So I'm moving, so what we are doing is that we move the filter and we compute the correlation. And you see that, so what you obtain is a function of time of the correlation. And actually when there was a signal, which is here, you see that the correlation function is maximal. And this is how you apply, so we compute the correlation. The signal to noise ratio is just the correlation divided by the power spectrum. And we apply a threshold on this function. And when we have a signal, it must be over the threshold. And this is the way we detect a signal. So this is the basic, principle of match filtering. Yeah, again, so the summary of match filtering. Where, so what we do, so we multiply the data by the waveform, and we divide by the power spectrum. The point is now which waveform to use. Because I'm telling you, I want to look for a given signal, but which one? When we look for compact binary system, we don't know the masses, we don't know the parameters. And depending on the masses, depending on the angular momentum, the spins of the black holes, the waveform is going to be different. So what we have to do is not to take only one waveform, but to try any waveform that is actually accessible by the LIGO Virgo detectors, which is where we know we can detect in our frequency band. So we don't compute the correlation with only one waveform, but with a template, a bank of templates. So the waveform is called template. And we're going to use many of these waveforms. So the point is which one? So again, it's another representation of match filtering. You take your data, you multiply by a template, you divide by the noise. And you need to test many templates, many waveforms. And the main parameters are the masses of the two compact system and the spin, the angular momentum. It's also changed the waveform. So here you see actually what has been used for what is currently used or what has been used last year. I think it concerns only, the template bank is always changing. You see each point represents a waveform. And you see that in that case, we were using something like 200,000 templates. So it's not one, but it's, so it takes some time because you have to compute the correlation for the whole data set with many templates. And depending on the mass range, actually here you can see that in this search we were looking for objects between 1 solar mass and 100 solar mass for the two components. And depending on the mass range, we have different type of waveforms, because the waveforms are produced, if I can say, by the different theory groups. We take what is available in the literature, but they are correct for it. Depending on the mass of the system, they are more or less accurate. And so what we do in reality is a mixture of different type of waveforms. And so what exists right now, and depends on, I'm going to come to that. There's two things in gravitational wave data analysis. The first thing is we need to detect a signal. We have the data, and we need to extract the data, extract the signal in the data. And the second thing, once we know that there is something at a given time, is to estimate the parameters. And the two problems are separated. The reason why is that for pure detection, we don't need the most accurate waveforms. We just need to have enough information about the signal to be able to see it above the noise. But we don't need accurate waveforms. While for really find the parameters of the source of the object, we need the most accurate waveform possible, which is available on the market. And of course, things have changed over time. Here you have different type of waveforms that are currently available on the market. So it's a subject for at least 1 hour to talk about waveforms. But the validity of the waveform depends on the mass ratio and the velocity of the system. If you are at the very end, very close to the merger, you're going to be relativistic. And then while you're at the beginning of the coalescence, you're not, you're very slow in that case. The post-Newtonian waveforms, which is the first approximation. Yeah, because one thing I did not mention is that the two-body in GR, the two-body problem in GR is not fully solved. So there is only approximation to the solution of the equation of movement of the two-body. It's the same thing for the gravitational wave, for the waveforms. And so we have only methods that approximate the solution. And the first method that has been developed and used for many years since Einstein is the post-Newtonian method. So this method is valid during the inspiral phase of the compact binary emission. It's not no more valid at the very end. During the merger, it's not valid. I mean, and actually it stopped before the merger. I mean, there is no prediction. The perturbation theory approximation are actually, those methods are valid, are accurate at the very end of very close to the merger, but it's not valid when you have equal mass system. It's a method that assumes that you have a test particle around a big one. And finally, you may have heard that 10 years ago, actually, the numerical relativity solution, the people trying to solve the Einstein equation using numerical relativity methods have been able to simulate the merger of a binary black hole. So we have waveforms coming from numerical relativity groups. And the point is that so far we have waveforms only in the regime where you have equal mass. But they are very useful, especially to calibrate the waveforms coming from another method called effective one-body, which is quite valid almost everywhere, except that it needs to be tuned for the merger. For the simulation of the merger, it needs to be tuned with numerical relativity. So just to tell you that we are using a mixture of all this prediction, and especially to extract the parameters of the data, of the source. In that case, the question of which waveform we use is very important, because if you change models, you see differences. Small differences, but you see differences. And this is what we call a systematic in the estimation. So, yeah. So I said earlier, after I need to accelerate. After the detection problem, you need to try to estimate the parameters of the source. To do that, what we are using is Bayesian methods. So that will, again, we take all possible type of waveforms, and we scan the whole parameter space. And actually, the parameter space is quite large. For a binary system, you have 15 parameters to estimate. The masses, the spin, plus the distance, the sky positions, the inclination of the orbital plane. So in total, you have 15 parameters to fit. So the Bayesian methods, where Bayesian methods is you need a model. So and this is exactly the case for binary systems. So it's well adapted. And you end up with estimation of the parameters like that. That means contour in the parameter space. The problem with binary system is that there are many parameters that are coupled. For instance, the masses, the determination of the masses. So you have the posterior distribution here, and you see that the masses determination is not very accurate. You have a region, and the two masses are, of course, coupled. So we have a determination of all the parameters. The distance, distance and the inclination angle of the orbital plane is something which is absolutely, totally degenerated, as you can see. Because depending, if your binary is phase on, you will have a maximal of signal. But if it's a little bit, it's no more phase on, it's equivalent to have a source which is further away from you. So you cannot distinguish between an orbital plane which is not, a source which is not phase on with a distance. So the difficulties of the, and that's the reason why, although we have sky localization, so this is sky, I mean, you have the sphere, the sky sphere, and the localization of the source with only 2 detectors, it's quite bad, not very well accurately estimated. Another thing which is very important is the determination of the spin, but I see that I'm very late, so I suspect I'm going to skip that. Here it's the result of the determination of the waveform using either a model method based on the waveforms, the template of waveforms, or just using a wavelet decomposition. That means a sum of sinusoid. Both methods gives very similar results.
Question?
Yes.
So this wavelet method doesn't assume anything about the signal?
No.
And the BB8 template is a matched filtering?
Yes, exactly. Yeah. So the spin, I'm going to, I think, skip that.
This was the first event, the data.
This one, I think this is the first event. Yeah, the first event. The spin, what I wanted to say is that if you have spin, if your black holes or your black hole in our case have spin, it's going to distort the waveform. I mean, it's going to introduce some modulation, so it has some impact. And why we want to measure the spin, the point is that it's very difficult to measure the spin because, again, all your parameters are coupled. So the estimation of the spin is not very accurate. So this is for our 4 events we got so far. This is an estimation of this, I mean, it's a representation in space of the 2 spin, of the 2 black holes in the 2 hemispheres. And what you see is that for almost all except one, the spin is compatible with 0. That means, but you see that is very badly estimated. I mean, but it's compatible with 0. So, and why we want to accept this one, where we know that at least one component is not compatible with 0. So one must have a little bit of spin. But in any case, I mean, what is clearly is that we are not in the regime where the black holes are spinning at maximal speed. It seems to be not the case, even if we not able to measure the spin accurately. Why it's important? Because it has some astrophysical implications, the spin. So I will try actually to finish with that, and I will skip the other slides. But now that we have events, we can do lots of things, especially astrophysics. And first thing we have done is to measure the rate of the binary black hole merger. So this rate is not well estimated. I mean, the error bars is quite large, but it's the first time we are able to measure. It's the first measurement so far. It's very important. And what I forgot to, we can say, I mean, we can measure the spin or try to measure the spin. And we have measured another thing which was very important and very surprising is that the mass of the system. Because so far people were thinking that what we were observing what was observed in terms of black hole is black hole with a mass of 12 solar mass maximum, or 15. That was the state of the art. But with this discovery of those binary black hole merger, I mean, the masses, I forgot to remind you, but the masses, no, for the first one, it was, forgot. Individual masses, it was 36 and 20 something. So it's the first time we observe stellar mass black hole with mass above 10 solar mass. And what it means is that they must be formed in some environment which is different from the environment we know very well, which is our galaxy, where because of the metallicity of the environment, you cannot form. At least this is what the astrophysicist always claims. You cannot form a stellar mass black hole of mass higher than 20 if you have the metallicity of our galaxy. Because of the solar wind, you have, when you form a black hole by the collapse of a big star, for instance. But if you have too much metallicity, so the opacity of the environment is too large. In that case, you're going to lose lots of material, and you cannot form a black hole which mass is higher than 15 maximum solar mass. So
what's the exact definition of metallicity? Is that, or how do you define metallicity?
The metallicity is actually I'm not totally sure of that, but I think it's based on the observation of the different stars you have. I mean, which kind of star you have in your environment, and the environment we know the best is our galaxy. So we know the composition of the star we have in our galaxy. But the point is that in the models, the people doing those predictions, these models to estimate how to form a black hole, they were saying, they were making a big assumption, is that all the galaxy in the universe is similar to our galaxy, but we don't really know. And so what we have learned with this system is that the most of the galaxy outside ours must be very different. So I think the metallicity is what we know about the stars, the composition.
Probably the main question, why can't we form those black holes by just merging of two?
Yes, so this is excellent question. And this is what people are trying to, there are different groups that predict how to form, because there are two scenarios right now about how to form a binary system of two black holes. Either you start with a binary system of two stars, and that exists, and at some point one will collapse, form a black hole, and at another time the other one will also end his life, collapse and form another black hole. So it's one scenario of formation. The other scenarios is I'm not really answering to your question. And then, so they will coalesce for millions of years, and then they will merge. And then you're supposed to form a black hole which is of higher mass. So in some sense, this is the seed scenario, is that you start with a stellar mass black hole and you form bigger and bigger black holes by merging. The point is that in that case, we should observe black holes of masses from few solar masses up to the supermassive black holes. And so far, this is what I was telling you, the only observation available was black holes of masses not bigger than 12 solar masses. So there was a famous gap between the 12 solar masses and the millions solar masses black holes. So this is the first time we observe black holes of 30, 40 solar masses. And now what we think is that there is no reason, and why people were really convinced. When I started in the field, many years ago, binary black hole merger, the event we have observed, people who were talking about them were considered crazy, because I remember I was told, but we know that they don't exist. This is what I was told, and actually, but it's not because you're told it does not exist that we did not look for them. We look for them and we find them. But in the community, that was, the LIGO discovery has been a big surprise, because it was the first time we observed such black holes, actually. And what I wanted to say about that is that, so yeah, I was mentioning the different scenarios of formation. Either in you start with an isolated system. You can form those a bounded system by capture, actually. But for that, you need a dense environment because you need to have lots of interaction. Because you need not only to have, to have two compact objects going close to each other, but you need to have a system that becomes gravitationally bounded. So there are different, so this is the two main scenarios, capture or you start with an isolated binary system of two stars. And the fact that, the fact that we have 4 observations, for the moment with these 4, only both scenarios are plausible with our observation. But the more, when we will have more events like that, we might, because of the mass distribution, we might distinguish, which scenarios is more plausible than the others. But for the moment, both scenarios are plausible. So what I wanted to show you as well is that, I'm not going to have lots of time, is that the test of GR, because this is another big subject that LIGO Virgo community is engaged on, but not only LIGO Virgo, there are lots of papers on that now, is to use events to test the prediction of GR. And so there are different tests we're doing. Especially we can test the dynamics because we are observing the signal for not a very long time, but for a few seconds. So we can test the evolution of the signal and test it with the prediction of GR. We can test if there is more than 2 polarization. This is something now we are implementing. And we can make some tests due to the fact, the fact that the event has been, has traveled up to Earth for a long time. So we can, for instance, test the Lorentz invariance using our events. And so this is the kind of test we're doing. So either using a parameterization of the waveforms or using the consistency between the different phases of the signal, the inspiral, the merger, and the ring down of the final black hole. So the GR prediction is very accurate, and with the data we can test the different phases. So the point is that so far no deviation. So the test we are able to do is not because we have only 4 events, and because the signal is quite short. It's a problem with high mass system is that the system enter into the frequency band and merge immediately. So we have a signal that lasts only a few seconds maximum. So it's not really accurate. So we need more events to accumulate more events to really reduce because statistically, with one event you can't, everything is compatible with GR at the point so far. But with more events, we can accumulate statistics and maybe say something about possible deviation to GR. So, yeah, and we were mentioning yesterday the residual test. You take your data and you subtract the best waveforms that match the data, and you try to see if there is any residuals, anything that is in the residual. So this is not the plot that is in our first paper we were talking about yesterday, but this is more accurate, actually more correct plot. And what we have seen is actually that for the first event, what we think is that, so first of all, there is nothing in the residual that looks like something that we could detect. And we think that we have fitted at least 96% of the signal. So this is to answer to the Copenhagen group controversy. I'm going to skip that. We do multi-messenger astronomy. That means we send alerts to different telescopes. And I just maybe want to mention So yeah, this is the current status of the detectors. This is the sensitivity of the detectors, the two LIGO in red and blue, and Virgo in purple, taken few days ago. So Virgo is trying its best to reach this level of sensitivity of LIGO. And as I was telling you, so Virgo should be taken data with LIGO. We will start doing that in two weeks, if nothing is changed, if we don't break anything in Virgo. Sometimes it happens. So, and we will, so just to, not really, that's the ugly part I was talking about the noise, noise understanding. Here you have the sensitivity curve, and so in blue, the measured sensitivity curve in Virgo, and you have all the estimated contribution of different noise. And in green, this is the sum of all the different contribution. You see, it does not match. That means there are noise we don't understand. This is what it means. And you see the complexity of the noise. It's quite, but there are people trying to understand the source of noise and reduce. We understand, we reduce, we understand, we reduce. And finally, I'm going to finish on the schedule of the different, what we should be able to do. So I was mentioning we are here. We will finish the O2 run end of August, we'll stop. There will be 1 year of commissioning improvement of the detectors, and we'll be back in 1 year, end of next year, for the third run, with hopefully a better sensitivity. That means more sources, and especially, and maybe new sources, not only binary black hole, because now it starts to be annoying to see only the same kind of signal. And what you see, so the design sensitivity of those detectors should be reached not before 2020 something. And at the same time, the Japanese detector should be also available. So it's going to be a nice time to do astrophysics and to do gravitational researches. And I think I will stop here because it's already late.